Hello everyone, my name is Pilar Cano, and I'm going to talk about flips in higher order Delaunay triangulations. This is a joint work with Elena Arseneva, Prosenjit Bose, and Rodrigo Silveira. First, I'll give you some definitions, starting with the Delaunay triangulation. Consider a point set in the plane S and a triangulation of the point set. We say that the triangulation is the Delaunay triangulation if the circumcircle of each triangle encloses no other point of S. For instance, in this case, the red circle contains no other point in its interior, which is the blue area. When the point set is in general position, meaning that no 4 points are co-circular and no 3 points are collinear, the triangulation is unique and it's the Delaunay triangulation of the point set. The Delaunay triangulation has been quite studied because of its wonderful properties. The first one is that it's the dual of the Voronoi diagram, also contains the Euclidean minimum spanning tree of the point set, maximizes the minimum angle of all possible triangulations, among others. The latter in particular is one of the most important properties because of its many applications in graphics, geographic information system, mesh generation, and more. However, the Delaunay triangulation is not always perfect. Sometimes, for instance, when you want to model a terrain in 3D, the Delaunay triangulation can ignore ridge lines or valleys, as in the figure. The left figure is the Delaunay triangulation, but we would like something more, as in the left. Still, the Delaunay triangulation has nice triangles, and we would like to still keep as well-shaped as possible triangles. For this reason, Gudmundsson, Hammer, and Van Crevel define what is a higher order Delaunay triangulation. Consider again the point set in the plane S. A higher order Delaunay triangulation of the point set, or an order K Delaunay triangulation of the point set, is a triangulation such that the circumcircle of each triangle encloses no more than K points in its interior. For instance, if we look at this example, the circumcircle of each triangle encloses at most 2 points. We also call this order K triangulation. So in this case, this is an order 2 triangulation of the point set S. However, in comparison with the Delaunay triangulation, a same point set can have many different order K triangulations. For instance, these two triangulations are two different order 2 triangulations of the same point set. They differ exactly by the two red edges. Now, we can define what is a flip graph. First, let me define what is a flip. Consider an interior edge of the triangulation and the two triangles that contain such edge, such that the two triangles define a convex quadrilateral. Then, a flip of such edge is defined by exchanging the diagonal of such quadrilateral by the other, as in this case. The flip graph of a point set is a graph which vertex set is all possible triangulations of such point set. And two triangulations are adjacent if they can be transformed into each other by exactly one flip. For instance, in this case, this is the flip graph of a point set of 5 points in convex position. In order to keep the relation between the Delaunay triangulation of the flip graph, first we define what is an illegal edge. Consider an interior edge and the two triangles containing such edge. Now consider the circumcircle of one of such triangles. If the circumcircle of such triangles contains the remaining vertex of the other triangle, then the edge is called illegal edge. In this case, the red edge is an illegal edge. A big result about flip graphs and the Delaunay triangulation is that any triangulation can be transformed into the Delaunay triangulation by flipping only illegal edges. This gives several consequences, such as that the flip graph of any point set S is connected, and the distance in between any two possible triangulations of such point set in the flip graph is at most n squared. In general, one can also study the flip graph of a subset of all possible triangulations, such that the triangulations have certain properties, such as triangulations that contains a perfect matching or a Hamiltonian cycle, among others. However, few things are known about the flip graph of order K triangulations. By the flip graph of order K triangulations, we refer to a graph whose vertex set is defined by all possible order K triangulations of the desired point set. Abe and Okamoto observed that the flip graph of order K triangulations of any point set is connected when K is at most 2, but they also show that it might be disconnected for K greater than 2. A connection between the flip graph and order K triangulations comes the flip graph of triangulations defined by order K edges. Consider 2 points. The edge defined by such points is called order K edge if there exists a circle passing through these 2 points and enclosing at most K points in its interior. Now, by definition of order K triangulation, notice that the edges of an order K triangulation is defined by order K edges, since the circumcircle of each triangle is a circle that passes through each edge of a triangle of the triangulation and encloses at most K points. However, the contrary might not be true. As in this case, we have 3 edges of order 1, but the triangle of such edges define an order 3 triangle, meaning that any triangulation containing these 3 edges will be at least an order 3 triangulation. Now, Avellanas and others showed that the flip graph of triangulations defined by order K edges is connected when K is at most 1, but it might be disconnected for K greater than 1. However, when the point set is in convex position, they show that the flip graph is always connected. Now, since we are interested in the flip graph of order K triangulations, in the particular case when the point set is in convex position, we know that if the flip graph of order K triangulation is disconnected, we can go from one connected component into the other within the flip graph of triangulations defined by order K edges. However, the result given by Avellanas and others implies an exponential upper bound on the flip distance within the flip graph of triangulations defined by order K edges. Now, we can finally state our results. First, we show that for any K, there exists a point set S in convex position such that the flip graph of order K triangulations of such point set is disconnected. Moreover, we give a triangulation that is an isolated vertex in the flip graph of order K triangulations of such point set and showed that K-1 flips are necessary in order to transform such order K triangulation into another. Then we show that this is a tight result, meaning that for any order K triangulation of a point set in convex position, there exists some other order K triangulation at distance at most K-1 in the flip graph of order 2K-2 triangulations of such point set. And finally, we show this for a generic point set for K up to 5. In this presentation, I will give ideas for the first 2 results. First, for the lower bound, we construct a point set and a triangulation of such point set such that such triangulation is an isolated vertex of the flip graph of order K triangulations of such point set. First, we take 2 points horizontally, U and B. Then, we add a point P1 close enough to such edge. Then, we take the reflection of such P1 with respect to the line, such that the circumcircle of U, P1, and B contains Q1. Then, we add the next vertex close enough to P1, such that it's outside the circumcircle of U, P1, B, and it's below the supporting line of P1 and B, as in the figure. Then we also take the reflection of such point, and we continue constructing such point set. Then we take the following triangulation, and we notice that this is an order K triangulation. In this particular case, this is an order 3 triangulation of the point set. However, this triangulation is an isolated vertex in the flip graph of ordered K triangulations of such point set. This is the flip graph of the order 3 triangulations of such point set, and the red triangulation is the triangulation that we exposed. In addition, we show that the red triangulation is at distance at least k minus 1 to any other order K triangulation of such point set. This concludes our first result. Now, let us give an idea for the upper bound. That is, for any order K triangulation of a point set in convex position, there exists some other order K triangulation of such point set that is at distance at most k minus 1. Moreover, we show that the flips required to go from such order K triangulation into the other requires only illegal edges. Now, let me give you a sketch of the proof. Consider a triangulation of a point set in convex position. Now, if there exists an illegal edge of such triangulation such that if we flip such edge, the resulted triangulation is still an order K triangulation, then the statement holds. Now, assume that the triangulation contains no such illegal edge, meaning that if you flip any illegal edge of the triangulation, then the resulted triangulation is no longer an order K triangulation of the point set. Now, we consider an illegal edge with a particular property, such that one of the subtriangulations defined by the particular illegal edge, in this case the red one, and the triangulation given in the gray area, is the Delaunay triangulation of such subset of the point set. Now, we flip such edge, and the resulted triangulation will be an order 2k minus 2 triangulation, but not an order k triangulation. Now, we use an induction on the number of points in the gray area, and we show that with at most m minus 1 illegal edges, we can reach to some other order K triangulation of such point set. Now, this concludes the second result, that is, for any triangulation different from the Delaunay triangulation of a point set and K at least 2, there exists a triangulation T prime such that there is a path between T and T prime in the flip graph of order 2k minus 2 of length at most k minus 1, where the triangulations defined by such path are given by flipping only illegal edges. In conclusion, we show that k minus 1 flips might be necessary for transforming one order K triangulation of a point set to any other order K triangulation of such point set. Moreover, we show that this is tight, in the sense that for any order K triangulation, there exists some other order K triangulation at distance at most k minus 1 within the flip graph of order 2k minus 2 of the point set for the following settings, that is, for k at least 2 and point set in convex position, and for k at most 5 and points in general position. Finally, as consequences, we obtain that any order K triangulation can be transformed into another by at most kn flips. And this also implies an efficient enumeration algorithm of order K triangulations using the reverse search framework of Abyss and Fukuda. This is all for today. Thank you very much for your attention, and hope you enjoyed this online conference.